Hey people, I'm going to tell you today about how waves or a wave or light wave can act like a particle or a wave. So how light can act like a particle or wave, okay? And really light acts just like this thing here. Can you see that you can both see the word wave, but at the same time you can see the word particle? That's exactly what light does, okay? So it can behave both ways, none of them is wrong, so it can be one and the other at the same time, okay? Just like as I told you, this wave particle thing. So we have a dual nature for light, okay? So it means that it can act one way or the other, as I told you. So the wave-like nature of light, the way that we see it, for example, is in the diffraction of light. So you already know that when you have any wave really passing through a gap, if the gap is smaller or about the same size of the wavelength of that wave, then the waves are going to diffract, they are going to curve as they pass through the gap, okay? The bigger the wavelength, the bigger the diffraction. So here I have a longer wavelength than in here, and that's why here the diffraction is very small, but here is quite big. Radio waves, for example, they tend to be quite large, and they can be diffracted even by the Earth's atmosphere, and that's how you actually can get radio and TV signals even if you live behind a mountain. So that's the diffraction, okay? In terms of light, light has actually a tiny wavelength. The wavelength of light goes from 350 nanometers, 10 to the power of minus 9, to about 650, 700 nanometers. So you need to have a tiny gap to see the diffraction of light, but it does happen. So when light passes through a gap about the same size as the wavelength of that light, okay, it spreads out, it curves, okay? The narrower the gap, the greater the diffraction. Now, we already know, in this topic we actually have been talking quite about this, that light can act like a particle as well. So, and this example here, for example, is the photoelectric effect. This happens as well as diffraction, but in that case, light is acting like a particle. So, in case you don't know what the photoelectric effect, go on the previous videos. However, light directed at a metal surface, the electrons absorb the photon, the electron's kinetic energy is increased, and the electron can escape the metal surface if the energy is bigger than the work function of the metal. So if the energy is enough just to get the electron to leave that metal. So, and of course, the work function of the metal does depend on the metal. So, if light has a dual wave particle nature, maybe other particles of matter also have a dual wave particle nature. So why would it just be light? So really the first step here to understand this, and I believe this one was Einstein, was, well, if light behaves this way, do other particles behave this way? So let's check. So Broglie was the one that brought this in as well, so I'm pretty sure Einstein helped. I think he was saying something like this. Yeah, he did. We saw in a couple of videos, but this is the guy that is going to help us today. So he said matter particles have a wave particle dual nature. So just like light, any other matter particles will have the same behavior, okay? So light is not special. And then he said the wave-like behavior of a matter particle is going to be characterized by the wavelength. And because Broglie is the guy that is bringing this up, he's going to call it the Broglie wavelength. This behavior is also going to be characterized by the momentum P, so wavelength, this is the symbol by the way, lambda, and the momentum P of the particle. So he said that the wavelength is going to be equal to h, Planck's constant, 6.63 times 10 to the power of minus 34 joules per second, divided by the momentum P, okay? So I can expand this part and say momentum is mass times velocity. So my Broglie wavelength is equal to h, the Planck's constant, divided by the mass of my particle times the velocity that the particle is going. So far, so good. So, evidence. So Broglie said all of this, but he really had to show that, right? So, The wave-like nature of the electrons was discovered when it was demonstrated that a beam of electrons can be diffracted, meaning a beam of electrons can act just like light particles do, and when they pass through a narrow gap, they will diffract. Okay, so this is a wave-like nature of something that we know is a particle. So here we go, electrons at a constant speed. You have a thin metal foil which is going to have a tiny gap, and then this was what was happening. So seeing from the side, the electrons were spreading out. Seeing from the front, you would get this diffraction pattern where you have the rings, okay? So you have the first ring, the second, the last one in this case. So you have the minimums and the maximums. We are going to talk a little bit more about the rings. So, first step, I had a beam of electrons in a vacuum tube and it was directed at a thin metal foil. Then on the metal is composed of many crystalline regions, did I say crystalline? Regions, each consisting of positive ions arranged in fixed positions in a regular pattern. So this is going to cause diffraction because there's going to be a gap for the electrons to pass through. So, the row of atoms cause the electrons to be diffracted, just as a beam of light is diffracted when it passes through a slit. So, by this experiment, Broglie just showed that any matter could have a dual nature, so could act like light, sometimes acting like a full particle, other times like a wave, okay? So diffraction, more about diffraction. So diffraction happens in certain directions only. So meaning you only have the rings in certain spaces and you're not going to have like a big blurry ring, if you know what I mean. So depending on the angle that you diffract, then you're going to have a place where you see diffraction, another place where you don't see diffraction, okay? A pattern of rings is formed on a fluorescent screen, so you can have a fluorescent screen. You can actually have different screens, but in this case it was a fluorescent screen. Each ring is due to the electrons being diffracted by the same amount, so each ring is caused by the same amount of diffraction. That's what I mean when I say diffraction happens in a certain directions only. I would not have rings if the electrons would just be diffracted all over the place. So missing rings means that the electrons were diffracted by that amount in that particular ring. Another ring, they were diffracted still, but by a different amount. The beam of electrons is produced by attracting the electrons from a heated filament wire to a positively charged metal plate, which has a small hole at its center. We saw that from the previous slide, I believe. Electrons that pass through the hole form the beam, and then, form the beam, and when they pass through the hole, they actually make the diffraction. So, I have these diffraction rings, right? Let me just show you. Here are the diffraction rings, and if I'm going too fast, always pause the video to take notes. Now, how can I change my diffraction rings? There is a way. So, this is again the diffraction ring. So this is a real image, okay? So I have, as you can see here, several rings. They are not all equally spaced. Some are brighter than others, but each ring was an electron that was diffracted by the same amount, okay? Now, I can change the speed of my electrons. So I can change the speed of the electrons by changing the potential difference. So if I increase the potential difference, I increase the speed that my electrons are going to pass through the hole. So if I increase that potential difference between the filament and the metal, then the lower part of my equation, remember the wavelength equals Planck's constant divided by the mass times the velocity. So the lower part of the equation gets bigger, meaning that my wavelength gets smaller, right? I think I have the wavelength here. Here it is, the wavelength, the formula. So I'm increasing this number, mass is the same, that's a constant, Planck's constant is a constant, so my velocity alone can change the wavelength. By changing the wavelength, I can have a different pattern, okay? So, if I increase the speed, it makes it the diffraction rings get smaller because the higher the speed, the smaller the Broglie wavelength, meaning that diffraction doesn't happen as well, right? You know that the bigger the wavelength, the better the diffraction, or the higher the diffraction. So this means that less diffraction happens, and therefore I get smaller rings. That's all actually for the wave dual nature. The light dual nature, so acting like a wave, acting like a particle. This is actually really simple stuff, but you know, if you have any questions, go back, see the video, review the video, re-see the video, if you know what I mean. Re-watch the video, that's better. If you happen to have me as your teacher, come and see me. So, see you next time. This is actually the end of this chapter, by the way, in case you're doing the chapters with me. So, see you next time, and we will then go on mechanics and forces. Bye!